Hello everyone. Okay, question two. Undoubtedly the worst done question out of the homework, and I'm not surprised. I mean, like, it's it's a good example of where they just tweak a mechanics question a bit, and it throws people off. And the thing is, as well with mechanics questions, and they're all like this, or most of the, especially the force diagram ones are, you're either going to score like 8, 9, 10 out of 11, or you're going to score 0, 1, or 2 out of 11. There's very little middle ground. Because if you get the diagram wrong, you get the initial setup of the equations wrong, and it all goes tragically wrong. Or you get the diagram right, you get the initial equations right, and you get the answer right. They're very much all or nothing kind of questions. Anyway, so I've drawn what I've got here, and I want to talk about a tan alpha equals 4/3 first, because I saw a lot of people telling me that alpha was 53.1, and actually you don't need to work out what alpha is in these questions. That you're better off. It's just, nicer mathematically to say, okay, if I know what tan alpha is, that means that I know that opposite divided by adjacent is tangent of the angle. So I've got a 3, 4, 5 triangle like this. I can work out the 5, of course, by Pythagoras' theorem, but that tells me immediately that cos alpha is going to be 3/5 and sine alpha is going to be 4/5. And that's bound to come in handy later in the question. So, always get into the habit of, if they give you a trick, what sine equals, what cos equals, or what tan equals, they've really given you everything there. They've given you the angle, haven't they? So they've given you everything. Okay, let's add forces to our diagram next. Now, this is definitely a bit where you want to be dead careful. Now, we know that's the tension in the string, so that's good. We also know that there's going to be weight acting down. That's great. So we'll put the easy ones on first. And let's actually label them. That's T, and that's 0.5 G. So far, so good, yeah? Now, here's where it gets tougher. Firstly, P, this ring, maybe I'll label it P. Hang on. P, this ring, is actually on the point of slipping up, which means friction must go in the opposite direction, down. Oh, let me do it in red. Friction's going to be going down as well, just like the weight. I'll just make it slightly longer so it's not right next to it. That's friction. So I'll call it F. It is at a maximum as well, so you can call it F max. I always like to write F max just to remind myself it's at a maximum. And you've got friction on there. Now, at the moment, just looking at this diagram, something is off to me when they're telling me that it's an equilibrium. It cannot be an equilibrium at the moment. The reason it can't be an equilibrium at the moment is because it should be going to the right, because the forces currently, they could be balanced in an uppy-downy sense, but in a lefty-righty sense, we're only going to the right. We've only got that tension pulling it to the right. There must be another force stopping it going to the right if it's an equilibrium, because it's supposed to be completely still, yeah? Well, that force is the reaction force. Why is it the reaction force? Well, R is a contact force. Now think about it like really, really close up. The ring, because it's being pulled in that direction, it will be that edge of the ring which is in contact with the wire. And in that contact, remember, R is a contact force, and it'll always be acting in the opposite direction to how the contact takes place. Because the ring is pushing against the wire, the contact force should come off in that direction. Yeah? R should be going in that direction. It's just like if you're standing on the ground is pushing up against you. Well, the ring, if you like, is standing on that ground in a sideways sense, and so the ground is pushing back that direction. But the other reason it's got to be like that, it has to be like that, is because it's in equilibrium. And so there must be a force opposing the tension or the component of the tension which is pulling to the right. And so I have to have an R over here. And that is the toughest bit to get the hang of, basically, in this question. There must be an R there. Once you've got that, you're in a really good position. It's an equilibrium, so we can say uppies equal downies, and that will be T cos alpha equals 0.5 G plus F max. But we've also got lefties equal righties, so R equals T sine alpha. We're now in a position to find the tension, I guess, because remember, F max is mu r. Have we got a value for mu as well? Yeah, mu is a quarter, something I forgot to write down. Mu is a quarter. So I've got mu there. And so what I can now do is say, well, F max is mu r. So what I could say is, well, let's write that down actually. F max is a quarter r. And r is t sine alpha. So we've got t cos alpha, using the first equation, equals 0.5 g plus F max, but F max is a quarter r. And r, of course, is t sine alpha, so I can trade r for t sine alpha. So let's do that. So t cos alpha equals 0.5 g plus a quarter t sine alpha. Personally, I'd like to times everything by 4 first. 4t. Oh, I also want to swap my cos alpha for 3/5. I'm timesing that by 4, so that makes 2g. And this is going to be just t sine alpha now, which is 4t. Yeah, 4/5, 4/5 t. And then I think everything's fine. Take the t's over to be united. They want to be together. So that's 12/5 t minus 4/5 t. Well, that's 8/5 t equals 2g. And so t is going to be 2 times 9.8 times 5 divided by 8. And that's what I'm going to do now. 2 times 9.8 times 5 divided by 8. And it comes to 12.25 newtons. And you've got yourself 7 marks. Okay, the solving the equations isn't the difficult bit. It's putting R in the right place on the diagram. That's the difficult bit. Like it's, people often get that kind of stuff wrong. I totally understand why as well. Okay, for part B, find the magnitude of the smallest tension in the string, which will keep the ring in equilibrium, given that the string remains at an angle alpha to the wire. Okay, smallest tension, smallest tension. I draw the whole diagram out again. I know students will be annoyed with me doing that, but it's important. So let's just draw the whole diagram out again. Won't take a sec. We're making t as small as possible this time, which means that it could be on the point of going down rather than up, which is going to change the direction of the friction. And that's what's going to be different in this part. The friction's going to change direction because we want to make t as small as possible so that it's in equilibrium. And remember, t is just this one up here. That's t. And we want to make that as small as possible, but it stays in equilibrium. So if we make t just enough, then suddenly it should be about to go down, which means friction will be going up this time. And that's subtle. People won't like that as well, I'm certain of that. And on the ring, I haven't drawn the ring here. I'll pop it in a second. Some naff little. That's the thing. Your diagrams haven't got to be beautiful. They've just got to be instructive, and help you solve the problem. 0.5 g. R still going in the same direction. I'll just do that like that. R, T, and this is alpha. And let's draw in another color. There's the ring. Okay, so there we go. That's the situation we're dealing with here, and we're looking for mu this time. So it's going to be a very similar kind of setup. You're going to have for the uppy downies, t cos alpha plus f equals 0.5 g. But for the lefty righties, you're going to have t sine alpha equals r. And so we can find f there, we can find r there. Let's do that. Hang on a second. Find a magnitude. Yeah, smallest. All right, yeah. So we're looking for t. I beg your pardon. We're looking for t. Oh, and mu is still a quarter. Yeah. So mu is still a quarter. Sorry, for a moment now, I thought they were asking us to find a new mu value. But F max is a quarter r. So we'll sub that in. T cos alpha plus a quarter r. Oh, but r is t sine alpha, so a quarter t sine alpha. I hope you don't mind me doing that slightly quicker. Equals 0.5 g. T we can actually take out. Well, let's actually type in our cos alpha and sine alpha, actually. Probably easier like that. Okay, let's move it down a little bit. Okay, so we've got t times, I think cos alpha was 3/5. Let me just check on that. Yeah, T times 3/5 plus a quarter times T times 4/5 equals 0.5 G. Personally, I'm going to factorize out the T and do 3/5. Well, that's 0.6 plus 0.2. So that's 0.8 equals 0.5 G. And so T comes to 5/8 of 9.8. And I get 6.125 newtons. And yeah, do the appropriate rounding, but that's what T is. Okay, I hope question 2 makes more sense now. I know that's a tough question. It didn't seem like a straightforward question to me, but that's how it works. Anyway, keep up the hard work.